Right. So what I have basically explained here is that we had an issue because we didn't know how to measure the distances for different galaxies, and we have observed this nebula, which we now know as galaxies, but we didn't know how to figure out whether it's that belongs to our own galaxy or it's a different entity which is so far away from us. For that, there is a new method came for measuring distances, because you cannot use these parallax method to measure larger distances due to the smaller parallax angle. And this new method is called period luminosity relationship, which is discovered in 1908 by this astronomer called Henrietta Leavitt. And so what she discovered was, using this Cepheid stars, they have a regular period, and this period is related to the luminosity of that particular star, which is what we call as the period luminosity relationship. Once this relationship is well established, if you can find a Cepheid star in a particular location, and the period of that, from this graph, you can find the average luminosity, and from that luminosity, you can calculate the magnitude and then the distance as it is explained in this diagram. First, you find a Cepheid star, and then you use the diagram, which is the period luminosity relationship, to find the luminosity, and the luminosity can be converted into the distance by knowing the apparent magnitude of that particular star as well. And you can, for example, you can measure the distance to Andromeda galaxy in this way. As I have explained here, the only thing that you have to do is look for some Cepheid variable stars in that particular galaxy. Right. Now, you know that there was a debate between astronomers that whether these the nebula type structures that they are seeing at that time, whether they belongs to our own galaxy or it's a different galaxy. Now, when this new method came up about finding distances, one of these American astronomers, I guess all of you know him, Edwin Hubble, he took on the challenge for resolving this debate, right? Now you can see that how scientists are resolving the debates, right? It's not like, you know, only from words. So he used this period luminosity relationship very nicely to resolve this issue. So he saw that, okay, if we can find some period, these type of, you know, Cepheid stars in these nebulas, you can actually measure the distances there, right? Which will resolve this problem. And what he did was, he had a telescope with him, which is a 100-inch telescope or 2.5 meter diameter telescope in this location called Mount Wilson in Southern California. And actually this telescope is still there. And this was the largest telescope in 1920s. Now it is actually not. And he photographed Andromeda Nebula because it was the closest one for us. And you can see that still I am using this word nebula because we do not know, right, whether it's a different galaxy or not at this time. And he detected several Cepheid variable stars within that particular galaxy, right? Now, once you have this Cepheid stars, he carefully measured the period of these stars and then estimate the distance using the method that we have discussed. And he came up with an answer that the distance of this Andromeda Nebula seems to be 1 million light years away from us, right? Now, actually, there are modern ways. Now we estimate the distances, which now we know that this is around 2 to 2.5 million light years away from us. But this data or this information that he took by nicely exploiting this period luminosity relationship was enough to solve this debate about whether there are other galaxies outside our Milky Way, right? Now, 1 million light years is so far away distance compared to our distance that we measure within our Milky Way, and because of that, it was found that the Kurds who actually used to tell that these nebulas are different entity than our Milky Way seems to be correct. And this was the first time that we confirmed that there are other galaxies in the universe, right? By measuring the distance to the nearby galaxies, right? Now, while learning astronomy, you can see how scientists solve the problem, right? And this is the skill actually that you should develop as well, right? So you use a scientific techniques to resolve problems, and this is what actually will be important for you in future as well, right? Now, coming back to about galaxies, after resolving this issue, now we know that there are several billions of galaxies in the universe. Milky Way is just one of those, right? So you can see that our position in the universe is a very, very tiny position, right? And inside each of these galaxies, there are around millions or billions of stars, and galaxies also contain interstellar matter and something called dark matter, as we discussed, as I told you earlier. And all these things, stars, interstellar matter, and dark matter, these are actually held together by this gravitational attraction of stars and other matter that you have inside these galaxies, right? And apart from that, the galaxies are usually separated from each other by vast regions of mostly empty space, right? So they are not attached to each other, they are separated by vastly empty space, and because of that, we used to call these galaxies as island universes, because they are separated very clearly from one from the other, right? Now, while all these things are happening in 1785, actually now we know the shape of our own Milky Way, but the first attempt that somebody took to make a map of a Milky Way is around 1785 by this English astronomer called William Herschel, and he constructed the first 3D map of the Milky Way. And the problem is, when you construct a map of the Milky Way, you have to measure the distances to stars to map it, right? Now, but he began with an assumption, assuming that all the stars have the same intrinsic brightness, which means the absolute magnitude. So he thought that maybe all of them are the same distance. And then he measured the apparent magnitude of each star and then make a rough estimate of the distance, right? So he assumed one particular magnitude, absolute magnitude for all the stars, which is in fact wrong, right? We know that it is wrong. And then he measured the apparent magnitudes and then did some estimates for the distances and make this particular map right here. And you can see that from a yellow color is where our Milky Way is, which is, we know that it is not the correct way of doing it now, because we are in one of the spiral arms in the galaxy. But the problem with this Herschel's map is that he found that the Milky Way has a flattened disk-like shape, and he also concluded that the sun lies at or near the center. So that's why he put the sun right here, which is actually wrong, right? And the reason that he got everything wrong is actually a practical reason, because at that time, astronomers did not realize that when you observe something, there is something called extinction, right? Now, what extinction means is, I think I probably have discussed this with you in earlier lectures. This interstellar matter that you have in the galaxy will actually obscure or dim the light as it passes through, because when there are a lot of dust, basically in the interstellar matter, you have these dust particles, and what will happen is they will absorb some of the light coming from these stars. So actually the stars should be brighter than what we are seeing from Earth, but from these dust particles or from the interstellar matter, they normally absorb this light, and then you don't receive as much light as you expect, right? And because of that, normally these distant stars, when the stars are so far away, they have come to a lot of space that you have dust, so they are more obscured by than nearby the stars, right? And because of that, maybe some of these distant stars may be completely invisible, or maybe some of them are very faint, right? And because of that, sometimes we tend to see that the same number of stars in any direction within the disk of the Milky Way. But and this is why the sun appears to be at the center, because when you see same number of stars everywhere, we think that we are at the center, but we know that this is not true. And again, as a solution for that, there is a second type of variable stars that we call RR Lyra, and these stars are actually became very important to measuring these, making a map of the Milky Way, because these RR Lyra stars are very regularly vary in the brightness, and this is another kind of variable type of stars. And the important thing here is their periods are in a different range than those Cepheid stars that we use to measure the distances for the other galaxies. These RR Lyras typically had half a day to day in length in terms of their periods, right? So they don't have long periods. Their period is around half a day to 1 day, right? So we don't need to look for days to calculate the period for these stars. And the other nice thing is these RR Lyra stars have approximately same average intrinsic brightness. So they roughly have the same brightness. Intrinsic brightness means like the absolute magnitude. And we know that they are about 100 times more luminous than the sun. And because they have this similar average intrinsic brightness, which means their absolute magnitude is basically fixed, right? They don't change, right? So because of that, they became an ideal, stars to estimate the distances in the Milky Way, right? And this is, if you compare these two types of Cepheid variable stars and RR Lyras in the same diagram, you can see the Cepheids are right here. This is what we have discussed in the earlier slide, which was very helpful to figure out the distances and discover the other galaxies in our universe, actually nearby galaxies. And then RR Lyra stars are somewhere here. You can see that their periods are kind of varying from 0.5 to 1 day. And at the same time, if you look at the y-axis, they kind of have a very similar intrinsic luminosity, right? And because of that, once you know period and the luminosity, you can easily calculate the distances. And you can see that in this class of variable stars, the time the star takes to go through a cycle of luminosity changes is related to the average luminosity of the star. And also shown are the periods and the luminosity of, I have shown you the period and luminosity of the RR Lyra stars. So once you know these two components, as you know, like in the Cepheid stars, you can use that to measure the distances. And by the way, these RR Lyra stars are often found in globular clusters, right? And these, I hope you remember what globular cluster means. Globular clusters are actually, we learned about two types of star clusters, open clusters and globular clusters. Globular clusters have, kind of older stars, and they have this spherical shape. And most of these RR Lyra stars are actually found inside these globular clusters in our own galaxy, right? And in 1970, once they have this relation about the RR Lyras, with this shapely identified around 93 RR Lyra stars in around 93 globular clusters inside our Milky Way, right? Now this allows you to measure the distances to these clusters. And once you find the distances, one thing that he found is that these clusters were having this spherical shape. I think we have discussed this earlier as well for the globular clusters. And he was able to estimate that the Milky Way is about 100,000 light years in diameter, and Sun was not at the center, right, from this method. And he estimated that the Sun was about 25,000 light years from the center of the Milky Way. And here is the map that he made, and you can see that this map makes more sense compared to the previous map. Right. Now, now we know that this was kind of, the history and how astronomers approached to different problems that they had about, finding the shape of the Milky Way and finding the other galaxies. Now, when you look at the structure of the Milky Way now, we now know that galaxies has 3 distinct components, right? And these components are, the first one is galactic disk, and the second one is galactic bulge, and the third one is galactic halo. Mainly, our own Milky Way is consists of these 3 parts: disk, bulge, and halo. Now, if you look at the disk of a galaxy, it has a large flattened shape with these built-in spiral patterns of stars and interstellar matter. And most of these Milky Way's young star-forming regions and interstellar matter are actually found in these spiral arms. And this is actually very common in almost all the spiral galaxies. You will see all these star formation and new stars in these spiral arms, right? So I have actually personally observed these things and have experimented with those, and I have clearly seen that, like H alpha lines, which help to look at star formation, are mainly concentrated in these spiral arms of the galaxies. And then you have the galactic bulge, which is relatively small and spherical in shape, and that lies the center of the Milky Way. And this is a kind of a dense region, the bulge, and it contains, different types of stars and interstellar matter. And then you have the halo. Halo is very large and spherical, and this halo actually made of relatively older stars, and also very little interstellar matter. And you can see from this diagram everything that I have described. This is, you have the galactic center right here, and this is the disk of the galaxy from the pink color, and from light blue color, this spherical part right here close to the center is called the bulge. And this halo is very large. You can see that halo goes around. That's a very large component, which has mostly older stars and also dark matter. Most of the dark matter is inside this halo. Right, now, if you go to more into details about the Milky Way, this central region of the Milky Way bulge is called the nucleus. And this region contains very high density of stars. So that's about the center of our own galaxy. And the one thing is that this nucleus of the galaxy, which is located at the very center of the galaxy, it's difficult to see from the optical light because there are a lot of dust around it. That optical light scatters from the dust, and because of that, we used to use a lot of infrared light to look at the central region of the galaxy, right? So when we observe this central region of our galaxy, we have seen something very surprising. That is actually when you do these observations of stars very close to the center of the nucleus, it indicates that there are these stars that are very close to the central region of the galaxy. So they are orbiting at very high speeds that we don't expect. Right? And when you look at the same region from the radio observations, which means using the radio wavelengths, using radio telescopes, it indicates that there is a bright radio source known as Sagittarius A, which emits a lot of radio signals in the radio wavelengths. Right? Now, these observations actually indicates that our nucleus of the galaxy is harvest to a supermassive black hole with a mass of 4.5 million solar masses. Right? That is what we have at the center of the galaxy. And almost inside almost all the galaxies, now we know that there is a supermassive black hole at the center. Right. Now this schematic presentation of the galaxy will show you these components. You can see at the center you have the nucleus bulge, and what you can see here left hand side is, it's kind of a face on view of the galaxy, and then you have different arms of the galaxy, Perseus, Orion, Cygnus, like that. And something that is probably important for you to note here is we are on the Orion now, right, on the galaxy right here. And if you look at the motions of stars in these different regions, you know that we have disk, bulge, and halo. There are three main components of our own galaxy. And if you look at the halo and bulge part, the stars that you have inside halo and bulge, they are actually rotating or moving in random directions. There is no, proper way of movements for the bulge stars in the halo and bulge. However, if you look at the disk, the galactic disk, all the stars orbit the center of the galaxy, and they are actually moving in an order, which means they all revolve into a certain direction very nicely. And the other thing is stars that are very close to the center of the galaxy move more faster compared to the other parts. And if you look at our own sun, it has an orbital speed of 240 kilometers per second, right? Now just think about, we are right here and we have our own sun that we think, which is so stable. But the reality is, when you compare to our galaxy, the sun actually orbits around our galaxy with 240 kilometers per second, right? And you can see that within 1 second, when we are talking, our galaxy, our sun is moving for 240 kilometers, right? And even in that speed, it takes 240 million years for our own sun to make an orbit, or go around our own sun. So it takes, so it go around our own Milky Way, it takes around 240 million years, right? Right, so this is a kind of a diagram that shows you how these stars move, and you can see that from this yellow color and this orange color arrows, it shows how the stars movements in galactic bulge and halo, right? Excuse me. And you can see that they are not in an order, so you can see some of the directions are to this direction and some of go here, like that. And the same situation for the bulge as well. However, if you look at the disk in this light blue color, they are actually moving, these galaxies are moving in a certain order. So stars are moving in a certain order around the galaxy, right? Right. Now let me, so these are few images that you can look at, and this is the center of our own galaxy using the VLA radio telescope. VLA means very large array of radio telescopes, because as you know, you probably don't know that the radio telescopes are sometimes not just one single dish, it's a collection of array of dishes so that you can collect all the light together. So it shows that there is a very bright source close to the center of the Milky Way, and we name that as Sagittarius A. And this is in fact the supermassive black hole that we have in the central region. And this is again a radio image of our galactic center. And here is the Sagittarius A again. And you can see that you cannot look at these parts using optical images, right? And here is another image that shows you the center of our galaxy and the tracks of the orbits of the stars measured for, around for 20 years, from 1995 to 2014. And what is important here is when you look at the tracks of these stars, so these are actually the central region of the image that you have is the central region observed from the Keck telescope. Keck telescope is located in Hawaii in the USA. And then you have superimposed the tracks of the stars around the central region. And what you can observe here is when a star getting closer to the central region, it starts to move very fast compared to when it is far away from the central region, right? And this indicates something. We can actually conclude about something from this image about the central region. And to have this kind of motion, a circular motion, you should have a very huge mass at the central region of the galaxy, right? And this is why we believe that there is a, not actually we believe, we now know that there is a supermassive black hole at the center of the galaxy. And this is why when you have these stars get close to the central region, they start to move faster, right? And another thing is that if you want to measure the mass of the Milky Way, you can actually measure it in a few different ways. But one of the simplest ways that you can think about is, as I told you in one of the previous slides, we know that our sun orbits the galaxy once every 240 million years, right? That we know the period. And then the radius of the orbit of the galaxy is 26,000 light years. And if you know these two factors, you can apply the modified Kepler's law, and we have discussed this law earlier as well, to find the mass of the galaxy. So that will be radius to the power 3 divided by period squared. And if you measure the mass in this way, you will get a value close to 100 billion suns, or 10 to the power 11 solar masses as the mass of the galaxy, right? And this is a rough estimate because we know that there are other matter beyond the solar system, right? Because our sun is in one of the arms of the galaxy, but even beyond that there is matter, right? Because of that, we cannot, concretely say that this is the mass, but you can roughly estimate. This may be the mass of the rough estimate can be done using this method. Now, if you look at, so that's what I have mentioned here. If you look at the mass, which is beyond the orbit of the sun, normally you can see stars and star clusters out to a distance of 50,000 light years. Now, our sun is, it's around 26,000 light years away from us. But when you observe, you can see around in our galaxy, we have stars and star clusters up to 50,000 light years away from the center, right? So their orbits, if you look at their orbits, this indicates that the total enclosed mass of about 2 times 10 to the power 11 solar masses, right? So you can see that it's around 2 times. You have measured only half of the mass when you measure the mass using the period of the sun and the distance of the sun from the center of the Milky Way, right? The other thing is, while there is very little visible matter further out, a small amount of gas enable us to measure the rotation speeds. Now, it is true that there is very visible matter when you go further and further away from the central region of the Milky Way. You will see less matter when you go to these outer regions. But there is small amount of gas in that region, and if you can measure those gases, we can get an idea about the rotation speeds, how they, what kind of speeds that those gases are rotating, right? Now, in general, what we expect is when you go outer regions of this galaxy, there will be less matter, and because of that, we expect a decrease of these speeds, rotational speeds, right? Speeds of these gas particles that are rotating around us, right? Around the center of the Milky Way. So this is, this is something from you can think from the basic physics that from the A level. When there is less matter to the outer region of the galaxy, those matter should, the rotational speeds, that means the speed that they are rotating around the galaxy, also should decrease, right? And this is what we expect. But very surprisingly, what astronomers actually observed is that these rotation speeds are instead of found increase slightly, which we never expected, right? Now, if you measure the distances, rotational speeds for these gas and or maybe some matter up to a distances of 100,000 light years from the center, instead of decreasing the rotational speeds, they start to increase slightly, right? And this is one of the very surprising results at that time. And this is the point that astronomers decided that there should be some kind of unseen component of this matter that we do not know, right? And this matter was named as dark matter, right? Once again, what has happened was from our general physics knowledge, what we expect is when you go further out, you cannot see much matter there. Because of that, when you measure the rotational speed of those gas contains in this outer region, we will expect that these rotational speeds should be decreased, right? But what we have seen from the observation is these rotational speeds are actually have increased slightly, right? Now, if that is if you want that is to happen, which means to increase of these rotational speeds, what should happen is actually there should be some kind of matter that we cannot detect from the wavelengths that we are using in the electromagnetic spectrum, right? Because we can detect radio, optical, infrared, so and so. But if we cannot detect something from those wavelengths, I mean, there should be something that we cannot see, right? And this component is what we named as the dark matter. And this is the place where you start talking about the dark matter, and this graph actually nicely explains it. Now, here is the center of the Milky Way, and you measure the distances to the x-axis, and then you measure the rotational speeds to the y-axis, and this graph actually called the rotation curve. And you can see that it makes sense when you go out. If the visible matter, the amount of visible matter increases, you expect an increase of the rotational speeds. That's okay. And then once you go up to this point, you can see that the amount of visible matter goes down. So what we normally expect from the physics is that your rotational speed should also go down in this way. But what has actually happened was, after this point right here, there is not much matter that you can see, but there is small amount of gas. and which means you can use the 21 centimeter wavelength. I think I have mentioned about this earlier, to measure the hydrogen, amount of hydrogen that you have, right? Because that you have a lot of hydrogen, some hydrogen in this outer region, you use 21 centimeter wavelength observations to take this hydrogen and measure the rotational speeds. And once you measure, what has happened was very surprising that you see an increase in the rotational speeds when you go outside. And if this increase happens as this way, as in the observations, you should have some kind of matter in this region as well when you go outside that you cannot see, right? So that is the idea. And this invisible matter is what we called as dark matter, right? Now don't get confused, and remember that dark matter is this, and there is something called dark energy that we should talk separately, which is basically related to the, when you go a little bit more into the cosmology, but this is what dark matter is and how it is found. And actually now there are other evidences that we have that there is dark matter, but this is one of the primary things that came from the observations, right? Now when you look at these galaxies, there are actually useful ways of characterizing a galaxy by using their ratio of its mass to the light that you see, right, in the units of the sun's luminosity. And this is a very simple calculation that we used to call as mass to light ratio, right? The amount of mass divided by the amount of light, right? Now, if you think about our own sun, we normally define the mass to light ratio is 1 by our definition, because we are going to use that as the unit that we are going to measure this mass to light ratio for the galaxies. Now, if you have a galaxy with a lot of star formation still occurring, so which means you have a lot of light inside that, because when you have active star forming regions, they emit a lot of light, right? So that's why, you know, we can see the stars now. And because of that, those kind of galaxies, this mass to light ratios are usually between 1 to 10. So it's a number greater than 1. So that is because these galaxies have actually some regions that you have still with some star forming regions. Now, when you have older stellar population, so which means that you do not have much new stars forming, and typical examples are actually elliptical galaxies, because elliptical galaxies do not have much new stars compared to spiral galaxies. Their mass to light ratio is around 10 to 20. You can see that their mass to light ratio is higher, right? So which means you can see that the mass is, in order to become that number higher, your mass is larger, amount of light should be smaller, right? And that happens when you do not have active star forming, a lot of active star forming regions, right? Now this number can be, can be used as a rough value to get an idea about what kind of galaxy that we are looking at, right? However, this only refers to the inner part of galaxies, because when you go for the outer region of the galaxy, dark matter comes into play, which we have not seen, right? So that will add a lot of mass, but no light, right? And because of that, if you add this dark invisible matter into a galaxy, this mass to light ratio can be as high as 100, because you get a lot of mass without any light, right? Because of that. And this is normally used to decide sometimes the types of the galaxies that we are looking at. As you know, we actually have spiral galaxies and elliptical galaxies basically, and the other type is irregular galaxies, which means you do not have a proper shape. And if you look at So I have mentioned basic differences and similarities between spiral, ellipticals, and irregular galaxies. And as you see for the mass, it's roughly in the same range. And in terms of the size, the spirals, ellipticals sometimes you can have actually very large elliptical galaxies. And for the luminosity, it's, roughly in the same range. However, for the star population, you have both old and young stars in spiral galaxies, but for the elliptical galaxies, mainly you have older stars. So those are the basic differences. And if you look at the mass to light ratio in the visible part only, if you look at the visible part only, the spiral galaxies have low mass to light ratio because they emit a lot of light because of the new stars compared to the elliptical galaxy. However, if you look at the mass to light ratio of the total galaxy, including the dark matter, you cannot see any difference between spirals and galaxies. Both come up to roughly a value of 100. Right? So that's because of the dark matter dominates when you include the dark matter. Right. Now the question now we have is, now we know that galaxies have some kind of dark matter. Now astronomers have this big question now, what is dark matter, right? Now, what we know up to now is the current measurements that we have indicate about 90% of the Milky Way's matter is dark matter, which is interesting, right? Because we thought that we know everything, but it seems like 90% of the matter in the Milky Way is dark matter, which we don't know what it is made of, right? And we know that they cannot be normal stars or interstellar matter, because if those are normal stars and interstellar matter, we should be able to detect it in some wavelength at least, right? Because we have equipments to detect anything within our electromagnetic spectrum, but we cannot see anything from those within the range of the electromagnetic spectrum that we are using. There is a belief that there may be some stellar mass black holes, as we previously discussed. It's hard to detect the black holes, and because even you have this idea, you cannot explain it, because we know that these stellar mass black holes are thought to be relatively rare, right? To have, in this much of 90% amount is accounted for dark matter, so you should have stellar mass black holes very frequently, right? So which doesn't make sense. And the other candidate may be the brown dwarfs. Remember, the brown dwarfs are failed stars that we talked under the stellar evolution, and or maybe the large planets, right? It also seems very unlikely, because then you should have very large number of these objects to take account for this 90%, which is it seems to be not realistic. And the other candidate is actually white dwarfs. So you can see that we are looking at these faint objects to see whether they make sense. But the white dwarfs may make up a significant fraction of the dark matter, but we don't know actually. We have not proved any of these things, right? And maybe more exotic scenario may be subatomic particles like quarks, electrons, those kind of stars. But we don't know still what this dark matter is, right? And that is about the structure of our galaxy and how dark matter came into play, and how you measure the mass to light ratio and all these things. And apart from that, galaxies are actually, there is a system that we categorize galaxies. Normally, Edwin Hubble was the first one who actually came up with a system of categorizing galaxies. And he actually examines, hundreds of different types of galaxies with his telescope. And when he looked at these photographs, he found that there are some similarities in their appearances, right? And because from that, he divided the galaxies into three main types. We actually already discussed about this: spiral, elliptical, and irregular. And after that, he made this Hubble's tuning fork diagram by further classifying these galaxies into different subcategories, right? Now, what you have in this part of the tuning fork diagram are all of them are elliptical galaxies, right? So they are elliptical galaxies, and they are subcategorized into different categories like E0, E3, E5, E7, like that. So that's based on their shape, right? You can see that E7 is more elliptical and E0 is a round shape one, right? I mean, ellipticity is less, like that. And then S0 galaxies are somewhat in between ellipticals and spirals, right? So those are kind of in between. In fact, actually, there is one postgraduate student who is working on this in our department now with me to look at the formation of these type of galaxies, these zero galaxies. And then you have these arms right here. Inside arms, all what you have is spiral arms. However, these spiral arms are also subdivided into 6 categories. The main difference between when you go from left to right is that how these spiral arms wound in the galaxy. And you can see that for the SA type, these arms are very tightly and very closely wound to the galaxy. And when you go for SP and up to SC, they are loosely wound. You can see that they are, kind of little bit stretched compared to these SA type, right? And it is the same when you go from here to here in the lower arm as well. These are loosely wound right here, so tightly wound. And then when you go towards the right hand side, this is very loosely wound. You can clearly see spiral arms that goes towards the outward region. Now the difference between this arm and this arm is that there is a bar at the center for the spiral arms, right? Just give me a minute here. Right. And you can see that there is a bar-like structure right here in the lower arm, and there are no bars for these spiral galaxies. Now that's how you categorize the upper and lower, and then from left to right, the categories are divided based on how tightly these spiral arms are wounded, right? And right now, everything actually I have explained to you how this categorization is done is basically written in these 2 slides. So they have different differences and different similarities for the spiral arms and elliptical galaxies and for the spiral galaxies. Now Milky Way and Andromeda are both examples for spiral galaxies, and they contain a bulge and a halo. And then the appearance of a spiral galaxy depends on its orientation with respect to us. Because, when you look at from a telescope, you will see spiral arms. I mean, you cannot see from this very basic telescope. But if you look at from a large telescope and make a photograph, you can actually very clearly see these spiral arms. And I actually do not have time to show you a real photograph, but I mean, if you take an image, you will clearly see these spiral arms, right? And the appearance actually, there are some galaxies that we called as the face zone, which means you can see the face of the galaxy. So if that is the case, then you will use to tell that they are face on spiral galaxies, which you can directly see the spiral arms. And there are certain type of galaxies that they are aligned, that you will see they are aligned towards us, so that you will see that they are called edge-on galaxies. And from an image, I can show you this. By the way, this is an image of the Andromeda galaxy. So it has a catalog number called M31, and these are called like Messier objects, right? And there are 2 other galaxies you can probably see, right? One here and the other one here, very close to the Andromeda galaxy. And these are actually, this is the nearest, largest galaxy for us. I mean, it's the nearest bright galaxy that we have, Andromeda galaxy. However, we have some satellite galaxies close to our Milky Way. And these two galaxies, top you have M32, this one right here, and this is called M110. And these are actually satellite galaxies or dwarf galaxies. You can see when you compare the size of this galaxy. Size of these two with size of this galaxy, this is very huge, and comparatively if you compare, these two are very small and brightness is smaller as well. So they are like, you know, two faint galaxies. So these faint smaller galaxies are called as dwarf galaxies, right? And don't get confused with the normal categorization that we have with the Hubble classification. So it's a different way of categorizing it. These dwarf galaxies can also fall into spiral or elliptical, but they are, in terms of the size, they are small, right? Their mass is smaller as well, right? Here is an example for what I have shown you. This is what actually show you the one. This is called M100, and this has, you know, these spiral arms are very bright. You can see that these regions are, you can see bright because they have a lot of star forming regions, right? And this is called a face on view, that you can see clearly all the matter and the shapes and everything. And this is, by the way, also a spiral galaxy. However, this is an edge on view, which means you see only the edge, right? Because, you know, practically when you observe something from our from the Earth, you cannot change the orientation, right? So orientation will be there. I mean, if you see it in this way, then that will be a spiral galaxy from the face on view, and this is called edge on view, which means this is a spiral galaxy, but you cannot see spiral arms and those kind of things separately, right? And this is NGC 4565, one of the galaxies, and this is called M100, that came from something called the Messier catalog. And here is the different categorizations that you have for this Hubble classification system. And I have mentioned the information how these differences come from, which I already explained to you. And here is about those barred spirals, where you have the bar in the lower arm. And again, there is a face on galaxy called pinwheel galaxy. So I have put some of these pictures here just to give you an idea that there are different, you know, different galaxies that we already have a lot of information. So here is, this one is called NGC 1300. Again, a barred spiral galaxy. You can see this bar type structure right here, right? So when you get experience with these images, you can actually decide what kind of a galaxy is that, right? And this is an information about elliptical galaxies, where you have different types depending on the elongation or the ellipticity, so which I have explained here. And all this information you can relate to the Hubble tuning fork diagram, right? So that's what I have explained here. And here are two examples of the elliptical galaxies. Just give me a minute here. So I'm going to unmute for a minute to switch off this telephone. Right, so here are actually two giant elliptical galaxies. You can see that there is a giant elliptical galaxy right here, and there are some galaxies around this image. So this is a galaxy, and this is a galaxy. This one is a galaxy. This one is a galaxy, and this is a spiral galaxy. And you have a very giant elliptical galaxy at the same time. And you can see this halo part right here. And here is where you have dark matter and all this stuff, right? And here is again another elliptical galaxy. We believe that this may have here due to the collision of two galaxies. And some of you may have large number of questions like how I am telling that this is a galaxy and how I am telling that this is a large galaxy, those kind of stuff, right? Now, if anybody have actually any questions, feel free to ask, because if I'm going to talk about each and every detail, then I won't be able to finish it. Because of that, what I am telling here is just the main points that I want to stress. And this is a dwarf elliptical galaxy. And you probably have seen that in the tuning fork diagram, you have elliptical galaxies and spiral galaxies, and they are also subdivided into different parts. However, you will have irregular galaxies, so they do not have this proper elliptical or spiral shape. So they do not have a proper shape, so that's why we call them as irregular galaxies, right? Those are the main types of galaxies. And then you have this S0 or lenticular galaxies. Those galaxies are actually between ellipticals and spiral galaxies. There is a location that you have S0. They have some different properties, and the research are actually still ongoing to understand the formation of these S0 galaxies. And again, I have put the Hubble tuning fork diagram here, which is actually the previous one. There is no difference, but to end this part, so you can get an idea how these galaxies are subdivided into different categories and their properties. And apart from those categorization of galaxies, remember that there are two types that we again talk separately, that is giant galaxies and dwarf galaxies, right? So this is a separate classification, right? It's not belongs to the Hubble tuning fork diagram, but there are two types we called as giants and dwarfs, and this is based on the size and the brightness and the mass of a galaxy, right? If you have large, huge galaxies that are very luminous, we call them as giant galaxies. For example, Milky Way, Andromeda, these galaxies are giant galaxies, and in fact, they are giant spiral galaxies, and we have very large and very luminous galaxies, and they are normally called as elliptical galaxies, right? And you have giant spirals and giant ellipticals. And similar way, dwarf galaxies, they are very small in size, so they are called dwarf galaxies. And dwarf galaxies also have dwarf ellipticals and dwarf spirals, those type of, you can subdivide if you want. But giant means they are large, and then they have their brightness is huge and they have a huge mass. And dwarf galaxies are smaller, and their shape is, their mass is smaller and their brightness is smaller as well, right? And what would normally happen is, when you have a very large giant galaxy, around that you will normally see number of dwarf galaxies, which are smaller ones. Now, if you look at our own Milky Way, we have a giant galaxy at the center, our Milky Way, and it has these satellite galaxies or dwarf galaxies, both names because of the same thing. And the closest galaxy that we have is the Canis Major dwarf galaxy. It is an irregular dwarf galaxy. This was discovered in 2003, and you can see not long ago. This is why this field of galaxies kind of a little bit new. And this is around 25,000 light years away from us, 42,000 light years away from the center of the Milky Way. Now we know that there are at least 16 dwarf galaxies in the orbit around our Milky Way. Right, so two of these most popular dwarf galaxies are actually large and small Magellanic Clouds. They are visible to southern hemisphere, and both these galaxies are dwarf irregular type galaxies. They are very close together on the sky and can be seen with the naked eye from the southern hemisphere as well. And they were first recorded by one of these crew members who call Ferdinand Magellan, as probably you know this story. And these are around 160,000 light years away from us. And both are 100 times more massive than most of the other groups. These are actually dwarf galaxies, but a little bit larger. And because of that, if you go to the southern sky, in the southern sky, you can very nicely see these galaxies at night. So here is the Milky Way band right here. And here is the large Magellanic Cloud, small Magellanic Cloud, and the large Magellanic Cloud dwarf galaxies. And this is how you would see it on the sky, right? As galaxies. And this photo actually is taken from this, the site of the CTIO telescope, which is located in Chile in South America. And right. And here is another picture of the two Magellanic galaxies visible from VLT telescope in Chile. Right, so we have now actually talked about galaxies and their properties, how they discovered, and the different, dark matter inside galaxies, and their mass to light ratio, how to find the mass of the galaxies, those kind of stuff. Now, apart from that, when you look at the galaxies, actually they are not alone, right? Like when we talk about stars and then we move on to galaxies, when we look at the galaxies, actually they are actually grouped together, right? We call them as galaxy groups. Now, if you look at our own galaxy, there are around 16 satellite galaxies, as you saw, and there is Andromeda galaxy nearby, and all these set of galaxies, we used to call them as a local group of galaxies, right? Now, most of these groups have at least 2 giant galaxies, and maybe some of these groups may contain several dozen of giant galaxies as well. And also these giant galaxies are usually accompanied with large number of dwarf galaxies, right? Now, when you look at one of these groups, all these galaxies are again gravitationally bounded together, right? So that's how these groups are made. So once again, galaxies are not alone. They are actually in the sky as groups in the universe. Normally you have, 2 or 3 or maybe few dozen giant galaxies. And then for each giant galaxy, there are, large number of satellite or dwarf galaxies together. And all of this set of, if you take all these galaxies, they make a group of galaxies. And we used to tell them this is a galaxy group, right? And if you look at the local group, you have the Milky Way and its satellite galaxies form a part of a small, so we have the Milky Way and its satellite galaxies, and we call that as the local group, right? And we have 2 giant galaxies, Milky Way and Andromeda, in the local group. And these 2 galaxies are separated by around 2.5 million light years. And each has a number of small dwarf companions. So they have, some dwarf galaxies around that. And this local group contains around 40 galaxies, right, in our group. So we are in the local group of galaxies, which has around 40 galaxies, including these 2 giant galaxies, Milky Way and Andromeda, right? Let me go to the next one. That is the clusters of galaxies. Now, some galaxies, as you see, found in larger groups. So this is we are in actually called a local group of galaxy, which is a small group. But there are some galaxies, they are found in very large groups. And these large groups are called actually galaxy clusters, right? And there are a number of galaxies that you see inside these galaxy clusters are huge. Some of them have, 200, 300 galaxies. Some have even 2,000, 3,000 galaxies, and even more than that, right? And these, galaxy clusters are very large in terms of their size and the richness. Richness means the number of galaxies that they have, and these, if you look at the size of these galaxy clusters, their size is around 15 million light years in terms of diameter. You cannot actually even think about their size. And the richest clusters contains around thousands of galaxies. In fact, I have seen galaxy clusters that has thousands of galaxies, and they are these rich clusters. They have very high density of galaxies at the central region, and then the most of the bright galaxies that they have inside the galaxy cluster are actually ellipticals, or that is zero type galaxies, right? And there is one nice thing about these galaxy clusters. If you look at each and every galaxy cluster, you often have a very giant elliptical galaxy at the center. So this is something very specific to galaxy clusters, right? For each galaxy cluster, if you take a photograph, you will see a very giant elliptical galaxy at the center that you can very clearly identify, right? I will show you some few pictures. And so what we know right now is 5% of all these galaxies are found in rich clusters. And here is an example. Actually, this is, so I took this image. It doesn't look nice, but this is a scientific image just converted into the JPEG. And this image is Abell 426 galaxy cluster. So you have this Abell catalog for galaxy cluster. And here is the center of the cluster that you can see a huge elliptical galaxy right here. And the shape that you see here is a little bit weird. So that is for the fact that the galaxy is very bright, that, you know, light goes everywhere, and there are a lot of objects around that as well. And this is an elliptical, maybe an elliptical galaxy as well. All of these are galaxies, right? You can see large number of galaxies here. Even directly, you can tell that they are galaxies, right? There are actually large number of visible galaxies that you have to change the scale a bit to look at it. As this is a JPEG image, you cannot do that. All of them are galaxies inside the galaxy clusters, right? And this is actually roughly around, I can't remember the distance to this particular galaxy cluster, but I will probably show that in the next one. This is a star, by the way, and this is not a galaxy. This is not a galaxy. I mean, how I am telling this, if you need to know, let me know, right? So I mean, there is no time for me to explain like each and everything. This is not a galaxy. This is not a galaxy like that. So this image actually I took myself. This is from this large 4-meter telescope in Kitwick National Observatory, and I guess 5 years ago, around February 2016, as far as I remember. And so I was actually looking at a different thing like star formation rates in these galaxies. But this is an example for you, and this is how the real science works. So that's why I show you a black and white image. All the image that normally you see, I actually colored the image to make it nice and I mean, looks good for the general public, right? But the real image that you take from these CCD cameras are they come up as like this, and right. Here is the same image, in fact, right? Same galaxy image, galaxy cluster image taken from the Sloan Digital Sky Server. And this is that central galaxy that you see right here. This is the same galaxy right here at the central region, that giant elliptical galaxy. And these are stars, by the way. Right, so that's end up the section that I want to talk about the galaxies and galaxy clusters. And if I summarize what we have done right here is actually we start talking about galaxies, and then we talked about the history, a little bit of history of galaxies, and how these Cepheid variables and period luminosity relationship is used once it is discovered by the Edwin Hubble to decide the first galaxy, which is the Andromeda galaxy. And after that, we talked about the central region and different properties of our Milky Way galaxy and different parts, and how the stars move inside the galaxy. And after that, we move on to talk about categorization of galaxies using the Hubble tuning fork diagram. And after that, we actually talk about the giant galaxies and dwarf galaxies separately, why you have those two names. And then moving to talk about the galaxy groups. First, we talked about the small groups, like the local groups that we have. And then I told you that there are large groups like galaxy clusters that have, large number of galaxies inside the cluster. And I showed you some of the examples, how these, galaxies looks like inside the galaxy cluster. And I told you that there is a giant elliptical galaxy at the center of these galaxy clusters, right? Now, your final lecture, let me share it. Right, I guess it's already 8:32, and you said, I guess you have a lecture at 9, right? Am I correct? You said that you have a practical or something like that. Is this correct? Hello. Do you have something at 9? Because if I start it now, then it will probably go up to 9:15 or something like that.
Yes, sir.
Amarasina, did you tell something? I guess I didn't hear you properly. Or somebody else, Chalani, Pavani, do you have lectures at some lecture or practical at 9?
Yes, sir. I have a practical chemistry.
Can you please put something into the chat window, because I feel that you try to talk, but for some reason I can't hear what you are telling. Because if you do not have lectures at 9, then I can finish off it, or if not, I probably have to take that last hour as well to finish it off. Okay, so you have practical, right? So then I am going to finish it right now. Our last lecture is about, so let me